and hi everyone. My name is Dr. Rohana binti Abdul Hamid. I am from Institute of Engineering Mathematics, Universiti Malaysia Perlis. Okay, today I will present our research which entitled Exploring Dust Particle Dynamics in Ferrofluid Boundary Layers, Impact of Stagnation Flow. Okay, for introduction, let's look at what is a ferrofluid and also dust particles. Okay, basically ferrofluid is the colloidal liquid made of nanoscale ferromagnetic or ferrimagnetic particles that suspended in a carrier fluid. Um, so basically ferrofluid is magnetic nanoparticles in some base fluid. Okay, um, in our study, we also consider dust particles because it is possible that any foreign particles, these dust particles can be present in the ferrofluid, in this fluid. Okay, so we also study about stagnation point flow. This flow is where the velocity of the fluid uh, P0. Okay, this is the destination point where the velocity for this flow becomes zero, okay, at a specific point in the flow fluid. So there are many applications for this destination flow, such as sediment transport, pollutant dispersion, behavior of water flows, and many more. Okay, these are some of the studies about stagnation flow in ferrofluid. Okay, in 2013, Khan et al. Consider stagnation ferrofluid flow in over a stretching surface. Okay, then in 2020, Yasin et al. Studied the stagnation ferrofluid flow with uniform magnetic field. Okay, next, in 2022, okay, in research study, Tashi et al. Considers or study the unsteady flow and with heat generation. Okay, and in 2023, more research study, Zainuddin et al. Studied this flow with mixed convection and also convective boundary layer. Okay, next, this some study of dusty ferrofluid. Okay, so in 2015, Sekar and Raju studied this dusty ferrofluid with Soret effect in dusty porous medium. Okay, next in 2022, Sandeep et al. Consider this fluid with thermal radiation. Okay, and last one, Hamid et al. In 2022 studied this flow with the inclusion of viscous dissipation and also overstretching and shrinking surface. So the objective of our study is to extend the result by Hamid et al. By considering the stagnation point flow. Okay, so for mathematical formulation, we consider a steady, incompressible, two-dimensional boundary layer, dusty ferrofluid flow, uh, with permeable stretching and shrinking surface. So in our study, we use magnetite ferroparticles with water and kerosene as the base fluid. Okay, this surface of the stretching and shrinking move with velocity uw. Okay, and So since we are considering stagnation point flow, so the free stream velocity is UE. We consider as UE. Okay. So this is the governing equations. Okay, where we have fluid phase and also dust phase. Okay. So we have this equation 1 until 6 with the initial and boundary conditions 7. Okay, then we solve the previous equations using this similarity transformation A. Okay, this all this equation, and then we transform the equations into equation 10 until 13 with the boundary condition 14. So for these equations, we solve using the BVP4C method in MATLAB. Okay, these are the results for this study. Okay, so figure 1 is the variations of the skin friction of magnetite. Where this is the previous study by Hamid et al. And this figure 2 is our study where we consider the stagnation flow. Okay, in this study, both figures, we consider or we varies the L. L is the dust particle loading, okay, the parameter for dusty, and then we varies this parameter. Okay, we can see that the effect of L is same in both figures. Okay. Um. So and then this axis for lambda values. Lambda is for stretching or shrinking surface, where positive values for lambda is for stretching and negative values are for shrinking surface. Okay. From these two figures, we can also see that in stagnation flow, the first solution increase. Okay, the stagnation flow broaden the first solution. Okay, in these figures, we this is the velocity profile where we uh, varies the parameters phi. Phi is the volume fraction of magnetite or the ferroparticles. Okay, we varies phi and also L. Okay, here is without stagnation flow and B is for stagnation flow. Okay, we can see also in both figures, we can see that the effects of phi and L are the same. All right, and then these figures is the temperature profiles where we varies the Eckert number. All right. So this straight line. Um, okay, this line is for base water. Okay, water we choose as the base water, and the dash line are for kerosene. Okay, we can see that Eckert number also effect of Eckert number is the same in both flows. Okay, but we can see that without the stagnation flow, the effect of Eckert number is more prominent. Okay, we can see clearly the effect of Eckert number without stagnation flow. Okay, as the conclusion, the result reveals that skin friction coefficient values for stagnation flow are greater in comparison without stagnation flow. Okay, um, next, Eckert number increase the temperature profile for both flows. However, its influence was more prominent in the flows without stagnation point flow. Okay. Okay, this implies that greater number values, greater active number values result in a more significant rise in the temperature profiles for the flow without stagnation. Okay, so that's all for my presentation. Thank you.